So again, welcome to Integr8. My name is Eric Davis. I'm the Technology Investment Analyst here at Automation Alley. My role within the company is to help small to medium-sized manufacturers with their cultural transformation to Industry 4.0. This session is going to focus on artificial intelligence, and the title of this session is called Data Science and Deep Learning Demystified. We'd like to thank our sponsor, Soothsayer, who's generally made it possible to host these important discussions today. Again, if you don't have the Wi-Fi network and password, it's up on the screen right there. At this time, I'd like to turn it over to Dr. Murthy Kolluru. He's a Carnegie Mellon PhD. He's a former rocket scientist, chief mentor at Soothsayer, and he's founder of one of the top data analytic institutes in the world, which is called International Global Engineering. So, thank you.
Thank you very much, Eric. Hello. Thank you very much, Eric, for the introduction. And thanks for taking your time to attend this session. Next 1 hour or so, I will do my best to make this session as productive as possible for the attendees. I'm going to focus on two major aspects. First half, roughly 30 minutes or so, I will talk about the technology of deep learning and machine learning. Of course, from a business perspective. I'm not going to do any calculus or programming in the session. What I want to talk about is why is deep learning so exciting for a business? What aspects of it actually make it so business friendly that you cannot but jump into the bandwagon? And the last 15 minutes or the 20 minutes, I want to talk about how an organization systematically can build a deep learning AI culture, DNA. These are primarily my experiences working with several organizations globally, and the success stories and failure stories I'll try to put together. So the first half an hour or so, the technical part. See, one of the interesting problems that machine learning community had to solve from the beginning is to define intelligence. I want to create artificial intelligence. Then what is natural intelligence? If I know that, I can actually create something artificial that works like that, right? Interestingly, that's not very obvious. If you do some soul searching, what is intelligence? All of us will come with 100 different answers. So before 1950, the scientific community generally agreed that ability to do math really fast is intelligence. If you look at the IQ tests that are designed, they more or less strengthen and corroborate that belief. So you had a human who could do 10 multiplications in a second. If I can build a computer that can do, or a calculator that can do 20 computations a second, I have an intelligent machine. Interestingly, by the end of 1950s, the low-end machines beat the super-performing humans in that aspect of intelligence. And then the community took a decision not to be satisfied, but to change the definition of intelligence, right? So what then they defined is the ability to learn from experience is the fundamental quality of intelligence. So if I can build machines that can learn from experience, if a doctor looks at a bunch of medical data about a patient, correlates with the past medical records that he or she had gone through, and say, hey, you know what, this should be the most likely condition, and maybe this is the most likely treatment that is to succeed, based on what they did before. A marketing manager looks at some tendencies or behavioral patterns of a customer and can say, hey, you know what, this customer is likely to churn out very soon because this customer looks like that other customer who churned out long back. That ability to look at data understand patterns and generalize it was considered intelligence for 50 or 60 years. And interestingly, by the end of 2010, the Watson era, people actually, machine learning community was able to develop algorithms that were working at the level or even better than a human. By the end of 2010, we had machines to which if you showed as many medical records as you showed to a doctor, the machine would make better decisions than the doctor in terms of predictions. That whether they had same thing with the marketing manager. The machine would know the churning customers before the human would know. And that target was actually one of those famous use cases where the machine knew that the daughter is pregnant before her parents knew. Algorithms became extremely sophisticated 10 years back. Then again, the community had a dilemma. Should we stay satisfied or should we change? And we took the decision to redefine intelligence again. And this time, the definition of intelligence is our senses. Can I have a computer that can see better than a human, write better than a human, speak better than a human, understand better than a human? Right? And the problem here is, for the problems that I talked about that were tackled between 1950 and 2010, as a learned human, we knew what factors we should look at to forecast whether a customer would churn or whether a patient had cancer. We knew we had to look at their cell size, we had to look at the platelet count, we had to look at whatever. There was some logic and experience. But if I ask you, hey, how exactly do you recognize your partner when you get up in the morning? I'm sure you are doing it with 99.9% accuracy, hopefully. Right? But how? What factors are you looking at? Length between the eyes, distance between the eyes, length of the nose, width of the nose. What are we looking at? We didn't know. That's so the problem is much tougher to solve. In the previous case, at least I knew what data I had to look at. Here, I don't have a clue of what I'm looking at, but I get 99.999% accuracy. I seldom fail. So 2010 onwards, the definition of intelligence is to crack this senses about which we know we have absolutely enviable accuracy, but we don't have a clue of how we are solving. And I want to start the journey there. And 2011, people actually had started a competition around 2008, 2009 to encourage scientists to get high accuracies in these senses. Stanford and Princeton, I think, jointly conduct this competition where they identified around 15 million images like this. Animals, birds, crockery, houses, faces, etc. And the goal is build a computer program that can learn from this, and they will keep around 1,000 images with them. It has to predict those 1,000, the right class, as accurately as possible. See, this is not a trivial problem even for a human. Egyptian cat, Persian cat, Siamese cat, maybe a human knows what a cat is, but most of us probably may not be able to distinguish between Siamese and Persian cats. So this is non-trivial problem, and in a human, the people who conducted those competitions, looked at those photos and images, had around 5% error. A regular human being had around 10% error. And let's look at what happened in this decade chronologically. And in 2011, the best performing machine learning algorithm had around 30% error, virtually making it useless for any industrial application. I mean, it was good for a paper publication in academics. The previous guy had 31.2 and we have 30.6, and we increased the accuracy by so much %, so people were doing it. In 2012, a rock star in deep learning, his name is Jeffrey Hinton, he teaches at University of Toronto. He came up with the first deep learning AI algorithm that brought the error from 30 to 15%. This was unthinkable. People said, wow, most of them didn't even believe it. They said, hey, you know what, he must have cheated. And they went and checked on other data sets and they found that this was working. That's when they said, oh, this is a new way of looking at the problem. And what he solved is not just accuracy. These algorithms had humans breaking their heads, coming up with those features that they were using in solving their machine learning problems. How do I recognize a Siamese cat? Yeah, the distance between the eyes must be an important factor. The angle between the nose and the mouth is probably another important factor. People were working on coming up with feature after feature that would enhance their accuracy, and they were nowhere close to human beings. What Geoffrey Hinton did was radically different. He just gave pixels to his program. The pixel values that your eye sees, just the same pixels that you see was the input to the program he wrote, and the accuracy improved by that 100%. So he solved two problems at once. Number one, he truly solved the sensory problems the way it should be solved, where human doesn't have a clue of what features should be used. And he got closer to a human accuracy. And that stirred up a revolution. 2013, University of New York University brute forced Geoffrey Hinton out of the competition. They just used much bigger computers, much more data, and they brought the accuracy error from 15 to 11%. See, by 2013, we had machines very close to a less skilled human. 2014, Oxford University said, hey, how many times that side of Atlantic wins? This time let me brute force everyone else out. And they used the biggest computer known on that day, largest and deepest computer, deep neural network with 19 layers, and got 7.6% error. So regular human being was beaten. Interestingly, they were runner-up. This side of Atlantic still had the winner. Google came up with what they called Inception Net, where they had a layer after layer after layer. I think DiCaprio's movie Inception was released. He had a dream within a dream within a dream, right? So they got inspired and they called their neural net Inception neural net, which had a 6.3%, 7% error. Now the expert human is at a threat. 2015, believe it or not, this happened within our lifetimes. Microsoft came up with the deepest neural net possible with 3.6%. So we had computers that could see better than human beings in 2015. So, and all this happened, mind you, with the same pixels that we use as inputs. In our lifetimes, what used to be a PhD problem here became an undergraduate homework here. Really, it became that easy. So that is exciting about this field. And this happened across 5 years. So now, in fact, computer vision as such, image recognition is not even solved as a serious research problem. It's over, it's conquered. What now people look at is, if I describe an image in words, can I actually have a computer draw it? I want to talk about sunset, computer understands it and creates a photograph of sunset from its data. So people are solving problems like that. And I'll talk about where it is relevant in business, not just in art world. But just give me a few minutes to walk you through where we are in the state of the art. Right. Text was another area, a sense that we wanted to beat. Translation was a huge problem for machine learning community. Again, people were looking at understanding a language in a very, very machine learning way. Hey, if there is an adjective before an adverb, then probably this is what it means. And if there are three gerunds, then this is what it means. A very artificial way in which no human works. And again, 2016, November 30th, if you had given to Google Translate this sentence, it would have translated it like this. Very, very machine-like, meaningless translation. December 1st, delightfully, it started translating it like this. Right? So, again, the beauty is no rules were given to the machine. Just feed it a lot of original language A, language B, let it figure out the patterns, let it figure out a scheme of translation, and let it come back with the translation. So language translation as such had graduated from a machine learning problem to a deep learning. And this year or last year, around 7-8 months back, Microsoft and Google both announced a human level accuracy in understanding speech. And we now have applications, more or less your Alexa, your Google Assistant, that work. They're getting there. They're almost there at a human level assistant accuracy. So, in the past 5 years, this new definition of intelligence, which relied on conquering senses, has been also achieved at a human level accuracy. So now we have systems that can perform mathematics faster than us, and that can extract patterns from data better than us, and that can see, talk, and understand text at our efficiency. Is this all about accuracy? If this is all about accuracy, maybe deep learning wouldn't have been as exciting. There are certain other things that happen in addition to achieving this accuracy, and one I already mentioned, which is the inputs that I am giving are not these scientific parameters that I learn with logic and experience, but it is just the same pixels or same words or same waveform of the speech that my sensory organs are receiving. So that's one major change that happened. People went ahead and looked at how a deep neural net actually is learning. It's a bit difficult to read this image, but if I give the pixels of a face, in the first few layers, it is learning these edges, color histograms, all the general features. And it is putting them together to create slightly more macro features like noses, mouths, eyes, and things in the face, which it is putting together to create the image, human image. So when they looked at what the system is learning, they realized that, well, it may be doing some math, but intuitively as we think, it is combining pixels to create some generic features, combining them to create slightly more complex features, combining them to create even more complex features to finally make a prediction. This ability to systematically learn features turned out to be a big boon for business. I'll talk about it in a moment, but I want you to note that while it gets the accuracy in style. It actually creates features, though it's very difficult to interpret what it is creating. If you spend your time going and looking at what it is creating, it creates these better and better features. By the way, some experiments showed that computers were able to figure out features that we never thought about. One experiment that people did was to have a computer predict what the quality of the cloth. For 40-50 years, textile industry, machine learning community was doing that, but machine figured out that the hump that is formed here is actually a very important feature which no fashion designer ever guessed. So the features it created were non-trivial. It came up with some things that we never thought about after several decades of hard work on that. Right, that's one thing. The second exciting thing is, when I look at an image as a human, I form a summary about it. Let's say there is a cat drinking milk. Actually, I'm summarizing. Let's say there is an image in which a cat is drinking milk from a red bowl. I don't think of it as cat, bowl, milk. I think of it as cat drinking milk in a red bowl while the master is watching the TV. Right? I form a summary. Same with text. When I read a whole paragraph, I form an imagery that stays in my mind. Machine learning community 5-6 years back didn't know how to form those summaries. Thanks to deep neural network, today we are able to have machines take an image, spit out that summary more elegantly than ever. And that summary is in numbers. And it turns out that when things are in numbers, it's extremely easy for us to solve. Though it sounds scary, but actually they are extremely easy to solve. Numbers are better than words because they are not confusing. 5 is 5. I know, love is not love. Right? So that's the problem, right? So it was such a boon for the business and for the scientific community that finally I have a way to summarize words, summarize text, summarize images. Google came up with some very interesting paper in 2013 where they actually learned the summaries of each of the English words in 50 numbers for each word. Actually, they described each word in 50 numbers. And when they took the number of king, subtracted the number of man, added the number of woman, they got the number of queen. So the system really learned how to summarize a word based on several concepts. See, you summarize a word based on several concepts, because if I said king, and asked you to think of a word, you would have thought about queen. Very unlikely that you would have thought about Czechoslovakia, right? That's because the words are conceptually stored in your mind. For the first time, we now have a way to summarize. And recently I read a fantastic paper. This is by a sales retail store in Germany called Rossmann, I think. It's a store. It has its outlets all over Germany. And one of the features, they were trying to forecast the demand of in each store, how much sales will happen in the next whatever days. And one of the attributes they took was the counties in Germany. Again, they didn't know how to represent a county. They just gave the store data and told, hey, call in alphabetical order. Let's call Bayern 1, Baden-Württemberg 10010001. They just gave some dummy representations, threw it into this computer. It learned some numbered summaries of each of these stores, each of these county states. And when they plotted those states, more or less what the machine predicted turned out to be very close to Germany map. Nowhere they fed in the Germany longitude, latitudes. They just gave the sales data in each state. It looked at it and said, hey, sales are very similar on similar dates between these two cities, different dates between these two cities, and hence this should be here, this should be here, and this should be here. And that turned out to be correct in a geographical sense. So today, thanks to deep learning, we have an extremely powerful way of creating features and summarizing information. Now, what does this mean to a business? Until 5-6 years back, solving a machine learning problem was a scientific endeavor. If someone asked me, hey, how do you think your session is going? If I were to wear my machine learning hat, I would say, hey, you know what? Let us collect a feedback at the end of the session. But then, you know what? Feedback, you are forced to be right. So let us conduct an examination before the session and exam after the session, look at the performance and categorize, visualize, and maybe have some other kinds of interviews, this and that. But if I ask there is one high school freshman friend here, Varun, if I ask him, hey, how do you know how my session is going? If he can be blunt with me, he may say, you know what, Murthy, when your session started, all of them were sitting tight up, and now 50% of them are dozing off. Maybe you're sucking. Right. Now, no machine learning scientist could use a feature that was so obviously used by humans to solve the same problem. We were forced to use things that if you are a manufacturing ops guy, if I ask you, is the machine working all right? First thing you don't do, you most likely don't look at how the temperature gradient changed at the knob in the past half an hour, or pressure fluctuated in the bottom. You say, hey, you know what, this is sounding different, open it up. But no machine learning problem had the flexibility to take the sound as an input. A sales guy in the store knows that the guy who is driving a Mercedes-Benz probably can be sold differently from a guy who is driving a second-hand broken car. But I was calling in my machine learning model Mercedes-Benz 100, broken second-hand car 010, 001, all are equal. So as a field, we were using very different approaches, features that humans were using in their, we were not using the factors that humans were using in their decisions. Today, we have a way, we are beginning to start building these inclusive architectures where, hey, you use an image, you think an image will help this solving a problem? Let's summarize it using a model, using a deep neural net. Let's summarize the audio, speech. Yeah, I can tell if two Chinese are fighting with each other. I don't have to learn Chinese, or I don't have to know whether they are using an adjective before an adverb or adverb after a gerund. I just hear them screaming. So let me use that. If you have a categorical attribute like state, let us summarize it better. So the ability for the business to use every kind of data that it has been collecting went up in the past 5 years. And please remember, what that means is machine learning, which used to be a specialist domain 5 years back, is now a way of solving problems, any problem. If you were to take one thing from this entire session, this is the only thing that I want you to remember. Machine learning is not a specialist domain to solve a few problems. This is an alternative way of thinking. A colleague of mine at Google said this, and I quoted it so many times, probably it almost now became my own quote. But he said, when other companies have a problem, they say, how do I solve it? Can I solve it using machine learning? When we have a problem, we say, how do I solve it using machine learning? As a mandate, we don't think about any other way of solving a problem. Any problem, electricity, lights are not turning on. How do I use machine learning to solve it? Google wanted a better logo. What would you do? Hire an artist. What did Google do? Show 56 million types of logos to around 1 billion users for 10 days and identified that shade of blue which was captured, which held people for the longest. Of course, their chief artist resigned after that. But still, that's another way of solving the problem. Right? So I'm not saying you have to get fanatic of not looking at any other way of solving the problem, but please note that if your organization has to make decisions, machine learning is an alternative way of making decisions. It is not a specialized field practiced by a few scientists, scary guys. No, it's not those math guys. It is everyone who takes a decision every day in their work who can be benefited by machine learning. And as a result, the models got simpler. Because I use much better, richer data, I can build simpler models. Another very exciting thing that happened is because of the systematic development of features. From an image, I develop these horizontal, vertical edges, color histograms, etc. I combine them to create some other slightly macro features. From there, I create noses and mouths. From there, I detect face. Now, if I want to build another machine that detects kidneys and livers, not dogs and cats, does it also need to recognize those edges? Does it also need to recognize those color histograms? Yes, of course it has to. So why can't I just take part of what I already built and then build only the residual stuff for this other problem? This revolution is called transfer learning, where one of the biggest complaints that business had with machine learning consultants or machine learning departments in the division is, hey, to solve the first problem, how much time you need? 6 months. How much money? $200,000. What about the second problem? 6 months and 200,000. Third problem, 6 months and 200,000. Because each problem needed to be dealt very differently. But now, hey, you know what? Once I solve the first problem, maybe 30% of it I can use for the second problem. Once I do 2 problems, maybe 50% of 30% here, 30% there, I can probably use it there. So now, suddenly, because of this systematic way of the learning of features, models are transferable. And this is a wonderful example. There is a team, this is not us, there is a research team in California that developed an algorithm based on the same dogs and cats algorithms that I showed to detect cancer. And in 3 months, they built the algorithm. That's what they claimed. 3 months, 3 engineers, 3 months. And their performance, the error rates were better than a panel of 4 human radiologists. That is mind-blowing. You take an algorithm that detects cats and dogs, retweak it, learn it, and build an algorithm in 3 months that can actually beat a panel of radiologists in detecting cancer. Unbelievable, right? So that's another major revolution. We not only can use multiple data types, we can use models from one problem to the other. And this is another major revolution. When Google came up with a translate engine, it said, hey, you know what? Let me build one deep neural network that summarizes English. Another deep neural network that takes that summary and unwraps it in some other language, French or German or whatever. Now, hey, this engine knows to convert a summary into a new language. Why should I give that summary only from English? Now let me take this down. Let me give an image summary. Let it translate it into, there is a cat drinking milk from Red Bull. Because all this knows is when I give a summary, it can give the answer. Chatbot, they use exactly the same thing. Question is language 1, answer is language 2. So suddenly, building a model had become a Lego block activity. You have each Lego block doing a certain task. And this is beautiful because for the first time, architecture, machine learning architecture is back to the business and engineers. Until, for a long time, it has been a scientific activity. Suddenly, hey, you know what? I have this block that does this block that does this. Can I put them together to get a solution? And that also built that systemic thinking. Hey, whatever I built for translator, can I not use the same for chatbot? Chatbot question is, I can think of it as language 1 and answer as language 2. Recently, someone asked me to build a sentiment analyzer. Huggies are more comfortable than Pampers, but are more expensive. That is the input. The output they wanted is Huggies, comfort, good, cost, bad. Hey, why should I actually build a sentiment analyzer? This is a language translation. I treat Huggies are more comfortable than Pampers and more expensive as language 1. Huggies, comfort, good, cost, bad as language 2. Let me translate 100,000 reviews in this language and feed it to the same old Google translator. The machine learning solution which they built for 8 months had a 40% accuracy. The language translation where I copied Google's model and had a few interns type the answer had 74% accuracy, and we accomplished it in 3.5 weeks. Right? So that is the change that business is seeing. Business now knows, business is beginning to realize, not it doesn't know, very few organizations know. Business is beginning to realize that, hey, this is a new way of solving any problem where I use the same data that a human uses in the machine. I use the same text, same images, same speech, same audio to solve the same problem. Number 1, hey, I can pick something that I built and reuse it here carefully. And you know what? Once I build multiple systems, I can put together these Lego blocks to create more exciting systems. This understanding, once an organization gets, their whole view of what can be done with deep learning changes. I kept hearing in all the sessions that I attended today, hey, do you know how I can use machine learning if I want to look at my manufacturing belt and but no, that's okay. That's a detail we have to get to. But first, step back. Hey, do people in my organization take decisions? Yes. How are they currently taking it? Guessing or using anything? If they are guessing, maybe this is a better way. So it's not about a specific business line that you have to think about when you think about deep learning. It's about a new way of solving any decision problem that you should realize. Now that means, how do you adopt it? And Google is blessed. They said, hey, if we have the DNA, everyone in the organization thinks that way. That whenever they have a problem, they only think about machine learning. How do you build that culture within your organization? what I want you to know is that everyone in the organization has a very specific role to play. And how am I doing it? I do. Oh, not bad. Okay, I do have. I just switched exactly at the right time. Okay, great. So, how I want you to know that everyone in the organization has a very specific role to play. Everyone. But I want you to know that that is not coding and programming. CEO, to become a deep learning organization, everyone in the company does not need to learn Python. That's a misconception that many carry. Many carry that this is only a technical job. In fact, in my experience, in adoption of deep learning, either finding a vendor or setting up a team of deep learning engineers is one step. And you know what? That probably is the easiest step. With so many MOOCs and education institutes, almost every engineer today is trained in some aspect of machine learning and deep learning. So that is not the challenge. It is understanding the role of every other member within the organization and training them, educating them in that. That is the challenge. So what I notice is executive suite. If I look at the executive suite, how to, in the morning actually I heard this question, how do I know which problem to work on? I think that's one of the most important tasks of a C-suite. They have to figure out how to draft an AI manifesto of their organization. Hey, for my organization, these are the low-hanging fruits. These are the tough ones. These, if I solve, I'll change the game. Now, what order I have to solve? How do I go about solving them? How do I go about, as in not how do I write the code, which teams I set up, which policies I set up, is a very important decision that the CXO should be able to do. And there are some frameworks and some tools that are available. Secondly, deep learning, having said that, of course, I'm only showing you the demo version of all the experiments, right? So, deep learning is an experimental science. Like in pharma, 8 out of 10 experiments fail. So, like in pharma, the organization has to figure out how to build that fail-fast culture. So, in a pharma industry, by the way, I was told by a few friends of mine that to create a drug, they spend approximately $4 billion. Of that, $3.6 billion is on failed experiments. So, the game, the formula of winning a pharmacy industry is kill fast, because 90% of experiments anyway fail. The sooner you kill an experiment, so the sooner you realize that you are failing, the better it is. And the incentive structures of the entire R&D teams or people involved in drugs is not dependent on how many successful drugs they make. It's dependent on how many quick failures they expose to the organization. So when you want to build a empirical culture like deep learning, as an executive, you need to know how to promote that fail-fast culture. What works for your organization? Now, product managers, this is interesting. Actually, in most organizations I consult or we work with Soothsayer and Safil we work with, one of the biggest reasons of failure is the unwanted friction between the product managers and the data scientists. It's very interesting because both don't understand that they are solving the same problem, but both don't understand that they think very differently about the problems. Recently, I was in West Coast working with one of the top companies, technologically advanced divisions of that company, and they were solving a customer churn problem. And they said, for the past 3 to 4 months, we have been working on this problem. So when I asked, can you define customer churn? They were not on the same, they didn't agree to each other. I mean, 3 months have already happened since you started working on the problem. You didn't define the problem that in a way that is friendly and understandable to a data scientist. And the questions I get is, why do data scientists think it's below their dignity to clean data? Why can't they just break their ego for once and clean the data? But think about data scientists. They are working on with 10 business units at the same time. That guy's data they clean, that guy's data they clean, that guy's data they clean. I mean, they are data scientists, right? You are making them data janitors. 70% of their time they are spending cleaning the data, and it's not cool. You go home and tell, honey, I cleaned the data. Again, I clean the data. Again, I clean the data. What are you doing, man? And you said you are a data scientist and you do math. No, that's the fact. So that understanding of what can be done by these guys, what can be done by PMs, what is the role of a PM? How do I translate a problem appropriately? How do I put the right checkpoints? How do I define what performance metric I should chase? There are stories on how companies have lost years of time and millions of dollars chasing the wrong performance metric. I was talking to a manufacturing company recently. They came and said, hey, you know what? We have a bad demand forecasting model. Okay, what are you using? This is one of the largest manufacturing companies you can think of. 250,000 automobile parts. So I said, what software? SaaS. SaaS is a pretty matured software. How can it be so bad? He said, no, they give 70% error. Okay. I told why? Then I looked at it. It's time series. It's established. People know how to solve it. What are the chances that SaaS is doing a bad job? Then I looked at some data. Some of their components are ordered in bulk, 100, 200. Some of their components are ordered as 1 and 2. On a 100 order, if I make a prediction of 105, I am making only a 5% error. On a 1 order, if I make a prediction of 2, I am making 100% error. And when you average, the average anyway goes towards the outlier. So there are these 100% errors that are pulling the error away. So I said, the model is perfectly all right. What you need to change is the error metric. When the numbers are low, use absolute difference. When the numbers are high, use percentage. So what error metrics are important and how do I productionize the system? I was talking to one organization, I think in this region. They said, hey, you know what? We built the entire model. The model is deposited here and the data that it uses is actually collected here. So we actually realized after building the entire model that we were working on data that we wouldn't have when we were actually making the prediction. Now we have to change it. So the failure of machine learning seldom is because of math. Mostly it's because of the lack of communication between these two teams. They need to be educated to communicate, not to code. And that requires a very specific skill. Right? And another, yesterday I was talking to a bank in Silicon Valley, and this is the tendency that I realize some organizations that are at the maturity level in machine learning already started realizing. They are saying, look, I have 3 divisions in my company. One is my center of excellence, these PhDs that do really, it's better if I don't touch them, right? They do the machine learning models. If I have them, I have them. If they give me something, I'm happy. If they don't give me something, they just are good poster boys. I myself am a PhD, so, please take it in a lighter way if there is a PhD in the room. Then there is a large chunk of business users. And then there is a IT team that productionizes. The problem is not increasing the numbers here. That's impossible for most companies. The problem that they are willing to solve is, how do I make this large chunk of business users take care of 70% of the solution? So that this end specialist team can only work on the remaining 30%. What does it take to convert my business analyst, my Java programmer, my SQL guy to solve 70% of any deep learning problem? And here is the greatest news probably for the business. Very many fields either develop really fast or become really easy. That doesn't happen simultaneously. Nanomaterials, that's my PhD area, is a fantastically fast developing field, but still you need a PhD to solve this. Deep learning, as I said, in 5 years, the error came from 30 to 3%, while the problem solution changed from a PhD to an undergraduate homework. This has become better and easier simultaneously. So it is actually a very sensible thing to have a large chunk of tiger teams in your organization who can solve 70% of the problem. and leave that 30% really cutting edge work to your, that COE or Center of Excellence that you have. And they will love it because they can then focus on what they are really good at, which is pushing the boundaries. These guys will do all the solvable thing. One of the organizations I met in West Coast, they call this lean lab. So they say, hey, my lean lab is where I am 3 years behind. And 3 years behind is a huge gap in this technology at least. I'm okay, I don't have to be cutting edge. I can be 3 to 4 years behind. I take the libraries that are matured enough and these teams actually quickly solve problems. It is the COE that is actually implementing all those theoretical concepts into solvable problems. Right? So every member and citizen data scientist, this is a Gartner kind term, where every other white-collared employee in the organization, your HR guy, your finance guy, your admin guy, their jobs are going to be affected. What do they need to know about data science? What do they need to know about importance of collecting a data? What do they need to know about importance of tagging the data correctly? Things like that are that is what they need to know. So the point that I want to bring about here is if you want to become a deep learning DNA organization, note that every member in your organization has a very specific role to play to make it a success. Because it is not just one area of specialization. Don't please approach it like that. It is a DNA change that you are looking at. Until now, what are the 3 types of problem solving that we know? 16th century, Newton came and introduced us a deductive way of solving the problem. Hey, you know what? For anything, I have these 3 laws. For my mechanics, I have 3 laws of motion. For thermodynamics, there are 2 or 3 laws. For everything, there are laws. From there onwards, any problem you have to solve, start from those laws and use math and logic to solve. That's what your engineers probably are doing to build components. That's one way of solving. It's called deductive way of solving. Second, take a guess. I think that's what MBA schools actually made it into a very systematic way. Look at all the contributing factors, use your general knowledge and take a guess. Educated guess. And the third way, look at the data and make the decision. This is the third way of solving a problem that stands along with taking a guess and doing an experiment. Right? So that is the culture that you want to build. So everyone, like how you expect every employee in your organization to go through the college physics, every employee in your organization senior managers in your organization to have the ability to take a guess. You should have every employee who is taking a decision to understand how to take decisions from it. And that is not coding. That is a cultural change. Right? I guess more or less that's what I wanted to talk about. I think I covered this. Now 2 slides I want to bring to you. What we do, Soothsayer and Insofi. We offer consulting and education solutions. We believe we have one of the strongest machine learning, deep learning teams in the world. 20 PhDs and 50 data scientists between India and USA. We are in Detroit and Columbus in USA. And that's a list, actually they all truly work. We didn't pick them up from them. Right? They all are with us. We do custom algorithms, AI solutions, corporate training, building center of excellence, advisory and architecture. So recently, McKinsey actually did a very interesting white paper. They studied around 400 different companies and found that in 70% of the cases, AI actually improved performance over that they were getting from other analytical techniques. So 70% of successful use cases was about building better models that had higher performance. And my guess is that is not because of math. My guess is because they now are using much richer data, text, image. They didn't explain how they got that, but I'm more or less certain that most of the cases, the success is because they are using data that a human would have used if he were asked to solve a smaller data problem. And 16% of the problems are necessarily AI alone could have solved it. There's no other technique to solve the problem. So the point is that I don't think the question is anymore, will my organization need data science? The question is to figure out how I am going to work better with AI and data science. Thank you. How much time? 10 minutes for question answers.
Does anybody have any questions?
So most of the growth of this is due to algorithm, maybe? Or the vision part?
Good question. His question is, because he didn't have a mic, I am repeating the question. He asked, hey, most of that growth, is it because of the algorithms? Not truly, yes, there was an innovation in algorithm front, but equally exciting was our ability to handle extremely large volumes of data. Today, we actually could train an algorithm on 15 million images. Now, if you think about a 1024 by 1024 resolution, an image is 3 million pixels. 1024 by 1024 is a million, then red, green, blue channel is 3 million. 3 million pixels are 15 million images, so that's trillions and trillions of data points, right? So today we actually have the capability to work on such large numbers. That's, I think, the big data, IoT, coupled with algorithm growth is what stirred that revolution. Right? I hope the silence is because you understood, but not because it went way, yeah.
Do you have any tools you mentioned that those effort is on the data cleaning?
Very
There are tools also. There obviously quite a bit of it requires that business knowledge and domain knowledge. If a value is missing, how do I add the data? So that is manual. And then that's what we actually encourage. The business users can actually do most of that work, so that the data scientists can focus on the algorithm and pushing the boundaries. And there are some tools, SAS has some tools, and there are specialist data cleansing visualization tools that people use. I can't recollect names of the tools right now, but there are. Data Robot, I think, has some really good features to clean the data. Yeah.
Short example of the radiologist. What's the radiologist view?
That's a good question. So, one of the hospitals in India, interestingly, this is one of the advantages of not investing in Watson. Because India is a poorer country, they didn't have Watson, and Watson, what happened was, after Watson was introduced, deep learning got developed. So solving that particular problem was easier in Watson. So coming back to it, one of the hospital systems in India had used to use 5 radiologists panel to take a decision on whether a person has a cancer or not. See, to detect it in stage 1 is extremely difficult. And if they detect, they can save the patient. If I detect in stage 4, there's not much that one can do. So they used to have a panel of 5 people discuss for hours to decide whether a person has stage 1 cancer or not. Today, they have only 2 members in that panel. One is a doctor, one is a machine. So now, doctors have a lot more time to actually cure the patient instead of predicting the patient. So it's actually, if you look at it, it's better use of time. So I don't, I'll come to you. Truly, you are right. There are one of the problems with neural net community in general is whenever they invent some task, that intelligent task and how to solve it, they say we created God. We found God red-handed, or we are better. Oxford published a paper that said in 126 years, all humans will be redundant. I mean, what kind of a paper is that? I mean, you can't even validate it anyway, right? 126 years later, I mean, none of us probably will be there to validate, so I can publish anyway, right? So the point here is, when someone else in machine learning solves a problem like that, they will say, you know what, I figured out a way to actually take the data to higher dimensions using kernel trick and apply a non-linear solution to solve at high accuracy. Half the world doesn't understand what they're doing. They say, okay, go ahead and do whatever you're doing. But these guys say, I caught God red-handed. I created brain. No, we just figured out another problem that humans can solve to solve it at the level of a human. So we figure out how to use that as an assistant and do our work.
So my question basically follows from that. So I was talking to someone from the same researcher, and this was probably about 8 months back. So what he commented was still based in New Jersey here, and like that, Watson is a text-based tool, so it is not an equivalent tool in industry to actually work on visuals.
Visuals, okay?
Okay. So if that is the case, in your example, where the radiology example, what kind of tool are you using?
No, this is actually, as I said, you can build it from ground up in 2 to 3 months. So maybe the specific case she's working had some different kinds of visuals. The reason why Watson didn't have vision-based thing is 5 years back we didn't understand it at that level. As you saw, all the growth happened in the past 5 years. So today, actually, it's a lot more easier to solve it. Visual recognition is if you have data, you can solve it, and I'm sure in her field also, it'll happen very soon. Yeah. So these are not even complex technologies. This is like a BS final year student. If she works or he works with a pharmacy or a doctor, they will be able to build it as a final year project.
Okay. So how much of the training the tool needed to actually be able to actually?
That's what I was talking about. If I were to start from the very beginning, I would have needed millions and millions of records, right? But because of the transfer learning, they were actually able to take the same model that predicted cats and dogs and tweak the last parts of that model with around 10 to 12,000 records. So it's not unbelievably data rich also. That's where the transfer learning really helps. You reuse the model that is built elsewhere on millions of records and use 10,000, 15,000 records to tweak it. By the way, it still requires a lot of engineering. So there is some complexity in it, but it's not as complicated as it used to be.
So some human has tell it that if these are the characteristics of the scan, then this is stage 1, stage 2, whatever, right?
A human doesn't have to tell if these are the characteristics. Human has to tell this is stage 1, this is stage 2. The beauty is they will figure out the characteristics. Previously, human had to tell the characteristics, and they were missing out some characteristics, etc. Today, you show an image, this is stage 1, this is not stage 1.
So they took the scans which are already diagnosed.
Exactly. Yeah, yes.
So you nicely covered how things have changed in the last decade or so. How do you think things will change in, say, the next 5 years?
This is really a tough question. Everyone has their own favorite. In my, let me first tell what others are thinking. Facebook AI head thinks that one problem we'll solve in the next 5 years is we will be able to create data instead of, he said, for a cancer, today I have to actually catch hold of a cancer patient, take an X-ray and say it has cancer. But in next 5 years, I'll be able to take probably 10 such things and ask the machine to generate one separate machine to generate 100 or 200 more X-rays of cancer patients. 100 or 200 X-rays that don't have cancer, tag them, and give this machine that data to predict it. There is one technology that developed recently as in last 11 months or so, it became productionizable to do that. Actually, it was able to create, looking at a bunch of humans, it was able to create another human photograph of someone who doesn't exist, but he is a human, right? So that, according to many, will be one of the future areas. I personally believe, because I am much more interested in business, the intrusive architectures that I showed, where previously you were only giving structured data to solve a problem. Though human was using image, text, and vision and all that today, I think we are beginning to harness the power of this technology to summarize all those types of data and feed it as a model. I think most businesses will adopt those inclusive architectures in the next five years or so to solve the regular business problems. So demand forecasting, I will actually look at the person and say, hey, most likely this guy will buy that product. And that's a hunch that as a sales guy I will have, right? I will actually have machines that will look at the same data and build the same hunch.
All right, we've come to the end of the time, so I'd like to thank you for presenting. If you guys want, you can download the. If you want to continue.